Hi, I'm Yeşim, and I've always been a little forgetful. I wish I could say I only forget small things, but no. I once forgot my university entrance exam paper, which changed my whole life and traumatized me for the rest of my life. And once I forgot the tickets in our Japan trip, hands down, it was the worst memory from that trip, considering the fact that a deer attacked us on the same trip. And the list goes on. Forgetting my cat, forgetting my luggage, forgetting my laptop at work. It has to stop. So I have a trip coming up in a month, and this time I'm determined not to forget anything. But instead of actually working on this chronic memory issue like a normal person, I did what any programmer would do in 2025, which is building an AI to do it for me. I decided to create a luggage tracker. Luggage. To help me keep track of the items I packed. This way, I wouldn't need to worry about forgetting things or realize that I forgot them at the moment. But before moving on, ChatGPT should have already been on this level, right? GPT is a little bit hallucinating. So the problem is now on me. I started by looking at object detection models. And as I'm looking, one name kept popping up, which was YOLO. YOLO is a computer vision model which can detect and identify objects by giving bounding boxes and class probability. So trusting its name, I decided to give it a try. It started quite well, but the more I packed, the more complicated things became. And I thought, YOLO has been around for a quite long time, so maybe I need something different. VLMs are AI systems that can understand both textual and visual inputs. And the field has been progressing so fast for the last few years that it has a wide range of different models. But for this project, I decided to use LlaVA. But first, let's see how it works. So here we have our image and vision transformer. And what transformer does is to split the image into fixed size squares called patches, then create embeddings, essentially vectors for each patch. So at the end of this process, we have our vision tokens. After that, those tokens go through a projection layer, which is a simple neural network that acts like a translator between the image and text. So after the projection, what we have is the information derived from image tokens that is mapped to the same dimensional space as language tokens. And within this step, model can now process image and text together seamlessly. So at the final step, those projected tokens are added to our LLM input, which already contains tokens from our text input. And it works like this. After some elegant prompt engineering, I started receiving the results. And it was great at capturing the general image, but then it started recommending things I didn't even know I needed. So I decided to take a mental break before jumping into another model. While on the ferry, I started thinking. What I essentially wanted was an AI tool that takes my packing video, tells me whether I packed everything, or shows what's missing. Once I get home, I created a 4-step pipeline, so the break did its job, I guess. And this is how it goes. First step is extracting the frames from the packing video. After that, I decide to filter out the frames where only a new item is added to the luggage. After that, the objects will be isolated from the pile of items. And lastly, those items would be detected by an object detection model. Let's see if it works. After extracting the frames, I decided to use YOLO because looking back to its performance, it was good at spotting the objects. And I already had the code. And YOLO worked quite well, reducing the number of frames significantly. We can move on to the third step, segmentation. And that's where I came across SAM, the segment anything model. SEM is an image segmentation model from Meta that cuts out the object even for categories it hasn't seen. Let's understand how it achieves that. Here we have our image input and prompt input. And in the segmentation models, a prompt simply means the input hint that guides the model toward the region of interest. It can be a single click on the picture, and if the user does not provide any prompt, then the model will assume there are prompts like clicks almost everywhere and calculate the prompt embeddings based on that. And after we receive those embeddings, image embeddings and prompt embeddings go through the mask decoder, which combines them to produce mask predictions. After a quick implementation, I get the segmented objects. Just what I exactly wanted. However, while doing those, I didn't realize how much time has passed. And I want to finish this before I start packing tomorrow. That's why for the final step, rather than looking further, I used Clip, since I had already learned how it works back when learning LlaVA. Clip is a vision language model that links pictures and words. And unlike object detection models, Clip performs well even on background-free images, like the segmented items we have, and isn't limited to a fixed label set, so it can predict categories it hasn't seen before. Before using it, let's briefly talk about how Clip works. On the image side, we have a vision transformer, and it's the same transformer as we use in LlaVA, and as you remember, we were receiving patch tokens as the output. And in Clip, our output is a CLS token, which essentially is a single learned vector prepended to the sequence of patch tokens. So CLS serves as an image summary. And on the text bar, we have a text encoder, which creates our text inputs embeddings. After that, all the image embeddings and text embeddings are projected into the same space, and the model's job is to pull matching text-image pairs closer together and push mismatched pairs further apart. Finally, the model measures cosine similarity between each image and caption, and the correct caption is the one with the highest similarity score, which in our case, this pair. And Clip did a great job. It detected object with very high confidence level. And I finished coding the packing list checker.